So shear strength parameters are C and phi. So how to find this C and phi? So that's why we can compute tau, which is equals to influenced by function of C and phi. So as explained, so in earlier studies, in earlier 1776, Charles Augustin Coulomb has taken some research over the shear strength of soil. He has come up with this. Actually, he was doing his research on retaining wall design, so wedge failure analysis. So he doesn't know what is the force which is going to act here. So he came to know, so tau is playing role. So this is what then wedge is about to give load over the retaining wall. So he wanted to find this tau. He has developed a simple test like this, a pulley setup. So one bucket. So this is a table. He has placed his soil here. So he has placed his soil here. Once it is loading with some soil, weight known. So this weight is known. So what is the load is going to be applied here. So this is an somewhat top portion and bottom portion. So this is an direct shear test which he has developed. So pulley. So once it loaded, so this is going. So this top portion will be movable in this direction. This bottom portion will be stable as connected with the table. So he is going to apply some shear force in this direction. Shear force in this direction, and the resistance will be developed. So in this failure plane in the opposite direction, tau. So this is how he has started the shear strength analysis for his retaining wall design. So what happens? So he has first taken cohesionless soil. Let me narrate it as a story. Cohesionless soil phi. So he know tau. Here it is phi. It is fully cohesionless soil. So cohesion is going to be 0, absent. So for a cohesionless soil, phi only be there. So what he has done? So let us consider an graph. Normal stress and shear stress drawn in a y direction, tau. By the way, let me explain with the help of friction. So come here. So frictional coefficient of friction. So frictional force developed in any direction is multiplied with friction coefficient into normal force applied, which means let us consider two different material. So this is material 1 and this is material 2. So between this two material we have a constant frictional coefficient F. So please remind this. So this is a constant friction coefficient. This is not going to be changed. So if you apply any lateral force, the friction force will be developed against this direction is an FF. So what is an FF value? This is normal load applied on this material, say any metal or wooden piece, whatever may be. So this is two different materials. The frictional force developing here is dependent on N, the load applied multiplied with friction coefficient. Say for example, this friction coefficient 0.6, the load applied is 10 Newton, the frictional force developed is 0.6 into 10, 6 Newton, the maximum friction force it can develop. So the force you have applying as a shear direction, at least 6 Newton you have to apply it in order to make this material 1 to move. So by the way, so the frictional force developed is entirely dependent on normal force. By the way, you are increasing it to 100 Newton, the force applied downward is 100 Newton, it is not going to be changed 0.6, but the frictional force it can develop is, frictional force is 60 Newton presently. So it can offer up to 60 Newton towards the force applied. So which means in the opposite direction. So at least you have to apply 60 Newton, then only this material above which may fail. What I am coming to say, so this paper and this skin has some friction coefficient. If I am applying normal force downward, so in order to move laterally, at least you have to give this 6 Newton force. When I am applying 10 Newton force, in order to my hand is move over this paper, I have to give some lateral force of 6 Newton. So by giving 100 Newton, my hand cannot move because 16 Newton has to be applied laterally to make a movement. So this is what a science behind this applied mechanics. I hope you have studied. So this is how also soil mechanics has the name of mechanics as added. So I hope we have understand this. So what Coulomb has done, if you give normal load over it by increasing n, n1, n2 by the way. So let us consider, so this is what an sample, soil sample, so having some cross sectional area. So this is a load going to applied. So normal stress is nothing but normal load divided by area you are going to give. So initially it is, say it is an 0.0 kg per centimeter square by the unit. So this is also kg per centimeter square because let us say it is mass. So the mass he is going to add, that is going to be play as an lateral force. So this is where he is going to place some many measured load. By the way, this is some measured in terms of kg is going to be applied. So this is normal load, say 10 kg applied for the area of 36 centimeter square. So by the way, whatever may be, say that is here considered as 0.5 kg per cm square is in first trial. So the shear stress is going to be developed. So he is keep on adding the soil material measured. So at 10 kg or whatever may be 10 or let us consider 12 kg he has added, and the soil has failed, which means the movement occurred. So here in order to find this FF, we take this as, so in this case we doesn't know 0.6. In order to find this 0.6, the N, you know, because it is you are applying the FF, it is what an frictional force, it is about to fail. So it's just a reverse process. So once this fails, that is an equivalent value of frictional force. This is known value, so you can find FF. So consider same in this case, you doesn't know FF. So as explained, frictional force divided by N, you get FF. I mean frictional coefficient. So this is an force. When this FF is going to be equal, so this is going to be failed. So what is the force you have applied to fail this is nothing but FF, and this is a normal load which you have applied, that is you know. So FF by N you get F. So by the way, 0.5 kg per centimeter square is applied in normal direction. So the lateral direction you are keep on increasing. By the way, 1 kg you are keep loading it, 2 kg you have loaded, presently 5 kg, 10 kg, at 12 kg it fails. So convert in terms of force by area, you get as stress, so you get some point. So by the way, increasing to 1 kg per cm square, so same thing, so it fails at different load as explained. So by the way, for different values we get a points like this. Once you draw a line like this, so this is what failure envelope. So it is a linear line. As you know, linear line, the equation is y equals to mx. So in y direction we have a tau, in x direction we have an sigma. So this is what angle of internal friction that I explained. So we measure particle interlocking system in terms of angle. So what is this line is going to be made with an horizontal plane is nothing but phi, angle of internal friction. So here m is nothing but slope. So tan phi will be the m slope. So tau equals to sigma n tan phi. It is an equation of failure envelope derived by Coulomb. For perfectly cohesionless soil, this is very major thing, very major thing. So we have seen cohesionless soil, so tau is sigma n tan phi. So this retaining wall may have a clay soil or mixed cohesionless clay or completely cohesionless. So let us see another cases when it is completely clay soil. So C has and phi is going to be 0 when saturated. Unless otherwise it is saturated, it may have some phi, there is a chance. So when it is saturated, phi is going to be 0. So you can see it in a liquid limit. Remember your liquid limit. So now, by the same way, how do we get failure envelope, sigma n and tau? So now what happens? This cannot be applied here. See, by the way, same, this is material 1 and material 2. You are applying some lateral force. Say it fails, just it moves, it fails. That is what I explained just before failure. It fails at 6 Newton. If you apply 6 Newton, it fails. Now you are increasing normal. Previously you have not given any normal load. Now you have given normal load 10 Newton. Now you are applying shear force, it fails at 6 Newton only, not increasing. If you are increasing to 10, it is also 6 Newton. What I am coming to say, this angle of internal friction is only dependent on the normal load applied, whereas the cohesion doesn't dependent on C is not dependent on normal force applied. It is not influenced by the normal load. So same, by the way, 0.5 kg per cm square, 1 kg per cm square, 1.5 kg per cm square or 2 kg, whatever the normal source increases, the tau shear value will not increase. So that is why you get horizontal line. So what is the equation of this? Say here y equals to some constant value, y equals to some constant value. So for the values of x, whatever may be, x equal to 0, y is same, 1 same. So for x different values, y doesn't change, y equals to constant. So this is a linear line equation. So where y is tau here, so y equals to, so this constant C, so here that constant is nothing but cohesion, tau equals to C is going to be the failure envelope equation for clay soil. Now say C5 soil, which is mixed, cohesion has cohesion and angle of internal friction. So mixed C5 soil. So this is a normal force applied and this is tau. So we get failure envelope equation like this. So this is known as failure envelope or strength envelope. So soil can give this much strength against this shear stress. So now this is an like a y equals to mx plus equation. So this, so as this made this intercept called C, so this is also intercept, we get cohesion. So this is what angle of internal friction with respect to horizontal plane it makes. So y equals to mx plus c. So y tau. So mx is nothing but sigma n tan phi plus c cohesion. So this is what a failure envelope. So that is why it also can be tau f plus cf. So this is an basic equation, tau f shear strength. So if you apply load, the shear strength will be mobilized at which it fails. So that is what shear strength is known as. So shear strength is sigma n tan phi denoted at subscript f, c denoted by subscript. So this is an usual basic form of the shear strength as found by Coulomb. He has done a very great job. So tau simply denoted by tau equal to sigma n tan phi plus c. So the shear strength of soil is not constant. So the shear strength of soil is increases when the sigma n increases, whereas your this phi and c are the soil characteristics, those are constant. So these are the soil characteristics for the particular soil which has some proportion. say C 40% proportion, so sand 50% proportion. So this varies. So this C and phi value may varies. So this but for a particular soil taken from the site, so this phi and C has to be determined. So and the shear strength is going to be generated is dependent on normal stress applied. So which means, so here let us consider this slope failure. This is a retaining wall failure. So the tau going to be developed in this direction is dependent on what is the sigma n in this direction. That is what the meaning of this equation. So sigma n, what is in sigma n? Acting on this failure plane will generate respective tau in this direction. So this is a major concept we have to keep in mind always. Now coming to the next part, Coulomb has done some work. So I have explained. So this is the work of Mohr on same shear strength. So he has some graphical representation. So he has done another great work Mohr has done. So here, so previously Coulomb has applied direct shears. So Coulomb has applied a direct shear. So and he found tau based on that. But Otto Mohr has a different theory. So he has taken a cylindrical sample. So this is going to be the stress applied. Let us say sigma 1. So this is this is sigma 1. So this is a lateral force applied in other directions. So this is a confining pressure. Say confining pressure. This is direct compression. So this is confining pressure. This is direct compression. So this is a sample. He is a typical example. He is going to explain with that more circle of stresses. So what he is telling, let us take the same graph, sigma n, and this is tau. So here sigma 1 and sigma 3 are normal directions. So this is an plane. So for this plane, this pressure applied is in normal direction. So this is a circle plane. So for this, the applied is in normal direction. So that can be taken as a normal stress applied. What refers to sigma 1 and sigma 3? Sigma 1 is a major principal stress. Sigma 3 is a minor principal stress. Principal in the sense, so in this plane there is only one stress. There is no shear stress in this particular plane. So when in a particular plane, when it is loaded, the only one stress is present. That is what refers to be as a principal stress. So here it is in maximum. So it is major principal stress. This is little bit lesser value comparing to sigma 1. So this is referred as a minor principal stress. So coming to the point, so he is explaining with help of this graphical representation. He is going to draw a circle. Let us say sigma 3 value 20 kPa. So this is going to be the value, say 100 kPa. Let us say we can draw a circle at 20 and 100. This is a circle we get. So what is coming to tell? He has taken a cohesionless soil only. He doesn't take C soil or C5 soil. He has taken only C5 soil for his analysis. So 5 represents cohesionless soil. He has done. So for a 20 kPa, by slowly increasing the compression test, at 100 it fails. So it is a test 1. At test 1, so for 20 confining pressure applied, so while slowly increasing the direct compression, at 100 it fails. So I have formed a circle. This is a failure circle or more circle of stresses we can see. So what he describes, at any plane, if you want to find, so this is what pole, by using this pole, if you draw any line over this point, touching point, so it is an say, let us say theta. So this theta, so what is the coordinate of this point? So we get sigma theta in x direction and tau theta, this is going to be y direction. So sigma theta, I mean, so by means, so if you draw this in this soil specimen, if you draw this theta plane, so sigma theta refers the normal load acting on this plane, whereas the tau theta refers, so if the soil is going to be slide in this direction, so this tau theta is refers tau theta developing in opposite direction to the sliding direction. So this is a great work of Mohr. He's telling, if you draw a circle, so consider a starting point, so which it is nothing but this is like a pole. If you attach any string, you can move over the circle at any point. So this forms a linear line. So what is an angle it makes? So if you take the same angle, so in your soil sample, so by the way this is a soil sample, in a soil sample of theta inclination angle, so this plane, so this circle plane has a normal stress of same the sigma theta value, and the shear stress of this tau theta value can be taken in this, as explained. This Mohr circle very easily he has explained. So this is what a stress is going to be applied. But by the way, he has failed to tell what is an failure plane it is going to fail. So at any theta, at any plane, you can find the stress using this Mohr circle, but yes, some of little bit lagging at what angle the soil is exactly going to fail. So that is why you can find tau f. He doesn't know what is tau f. So this is going to be fail. Tau f is our major concern. So he is told that at any plane you can find tau theta, but at what plane it fails, he is a little bit lagging in that. So he has done some tests like this. So this is test 1. So while increasing the confining pressure in lateral direction, so it is now increasing to 40 kPa, so 42, so we get next cycle like this. So at it increases, we get circle like this. So he is coming to derive a failure envelope as explained by Coulomb. So he is getting somewhat like this. So this is a failure envelope. So this failure envelope, so tau, this is sigma n. He found this tau is a function of phi. So this is a horizontal plane. So this is what phi we say. So he found this tau is function of phi, but he has not clearly explained it. So he has considered this failure of is an curvilinear, and also he doesn't explain what is an failure plane it is going to be failed. So that is also a lagging part of his. Then Coulomb has connected, Mohr has collected with Coulomb's theory. By the way, so this is an circle of test 1 we say. So Coulomb has given linear line, linear failure envelope, whereas this Mohr has curvilinear failure envelope. But Mohr has like to do some correction in his work, so he has accounted Coulomb's. By the way, he get, so instead of drawing a curvilinear line, he just draw a straight line which touching this. So we get C, and this is what phi value, and the equation of this as described by Coulomb C plus sigma tan phi, which refers. So, and that failure envelope as found by alpha. So, if you draw any, going to be a same value of alpha only. So, this alpha only, so your sample is going to be failed. So, this is an weak plane. Well done some tests. So, we get, so that is what, that is why, so at least you have an 3 or 2 circles in order to line this, in order to draw this line by touching this circles as a tangent. So, it meets this intercept, y intercept termed as C. So, it makes some angle nothing but phi. So, it is an failure envelope given by, so Mohr Coulomb both combinedly. So, tau equals to C plus sigma and tan phi. So, this whole figure represents the combined work of Mohr and Coulomb. So, Mohr work is in circle and Coulomb work is equation. So, we combine this, we get the whole setup. So, then only we can find the possible alpha failure plane, weak plane, this is going to be failed. So, now presently this point tells us the sigma theta, which is normal load, r and tau theta. So, this is a normal stress acting on this sigma theta is a normal stress acting on this failure plane. So, this normal stress will be influencing this tau theta. So, tau f. So, in this plane developed tau f. So, that is what given by this equation. So, once you found C and phi, you can compute tau. So, with a simple graphical representation, at this failure plane the soil is about to fail can be determined. Very simple work. This is a Mohr Coulomb equation. So, let me explain. Before that, modified Mohr Coulomb given by Terzaghi. Terzaghi has told that this tau value that you are going to find is based on total stresses. So, after his Terzaghi's work at 1936, this is modified into tau dash C dash plus sigma n dash and tan phi dash. So, here C dash and phi dash are in terms of effective stresses. What this effective stresses refers, actually this soil has some water. So, if you apply some pressure, so the pore water pressure will be developed. So, the actually we think sigma n acting on this plane is not the sigma n actual value. So, there is an pore water pressure develops pressure in all the direction, that is what somehow reducing the sigma n. So, total stress analysis is not actually taking place in the sample, that is what Terzaghi told. We have to always consider the effective stress concept. So, at the year he told us 1936, that after that we are following this in terms of effective stresses. So, tau dash equal to C dash plus sigma n dash tan phi dash. So, here C and phi are in terms of effective stresses, tau dash effective stress in terms of shear strength. So, here let me draw a circle like this, and this tau value is going to be, so when I am extending here, so this is phi value, that is also going to be a phi value, this is sigma 3, this is sigma 1, this is center of the circle. So, we get phi, and so let us name this A, B, C, and this point is going to be D. I'm drawing like this. This is perfectly 90 degree. So by the way, it is 90 degree. So what is this value? How to find this value? So this is nothing but sigma. So we get sigma 1 minus sigma 3 is nothing but dia of the circle. So sigma 1 minus sigma 3 divided by 2 is going to be the radius. So this 90 degree is nothing but sigma 1 minus sigma 3 by 2. A, B, C, D. Let us say this is E. So this is C. So here we need to find this. So I'm going to give us some derivation. So in order to find this E, so let us write sin phi equals to opposite side divided by hypotenuse. This is what hypotenuse. So 90 degree here. So this is hypotenuse and this is opposite side for phi. So sin phi equals to opposite side sigma 1 minus sigma 3 by 2. So divided by, so this is unknown value. Let us say x value, and what is the distance? So this is x up to E, this is x, and what is about this value leading up to the center? That is also unknown. So how to find this distance between E to the center of the circle? So how can we say that? So from this line to this line, we know that that is an sigma 3. So I am going to find this. So from here 0. So this is value sigma 2, sigma 3 is 20. So by the way, we have some values. So here to here it is sigma 3, and from here to here it is going to be the radius, same value, sigma 1 minus sigma 3 by 2. So sigma 1 minus sigma 3 by 2. So sigma 3 plus sigma 1 by 2 minus sigma 3 by 2. So sigma 3 full, it is half portion. So full minus half, we will get half. Sigma 1 plus sigma 3 by 2 is going to be this value, sigma 1 plus sigma 3 by 2. And this is what this value refers. Now this is C. So this is what C. Let us say consider tan phi. Tan phi is opposite by adjacent. So opposite is C, the adjacent is x. So x equals to C divided by tan phi, C times, so tan phi goes up and it turns into cot phi. So this value, say D, E, F. So this is say F, this is T. So this is what A. So AF, so this is value of EF. So AF equals to C cot phi plus this E value sigma 1 plus sigma 3 by 2. So I am substituting this. So in order to x C cot phi I am substituting, this is sigma 1 plus sigma 3 by 2. So this is an starting point of a derivation. So while doing some 3 or 4 steps, it is going to be convert into as sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. It is very basic simple derivation. You can refer any textbooks, this will be there. So it is derived by Bell's equation. Bell, so it is termed as Bell's equation. So sigma, this is finally going to be take in the form sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. So this is an same graphical method. It is in terms of numerical equation. So Mohr has explained everything in terms of circle concepts. in case of circle concept. So Bell has turned this graphical procedure into a numerical value. So by the way, if you give some sigma 3 value 10 kPa or whatever may be, so and it fails at some value of 100 kPa, so you can find C value and phi value without drawing this graphical methods. Say this alpha is nothing but failure plane, as you know. This has some equation 45 plus phi by 2 is an failure plane angle. This is also some little bit of derivation. So this two equations, sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha, alpha equals to 45 plus phi by 2. This is an major equation. You should keep this equation, and tau equals to c plus sigma tan phi as explained. So both are the very major equations will contributing to the shear strength of foils.